Welcome to this explainer. I'm absolutely thrilled to have you here. Today, we're on a mission. We're going to decode one of the most vital, yet honestly, often totally misunderstood mechanisms in networking. We're unpacking the hidden negotiations that keep network traffic completely secure from prying eyes. Let's get right into it.
Seriously, think about that for a second. The internet, it's a wild, inherently hostile place. Every single time your company sends data from a branch office to headquarters, or, a remote worker logs into the corporate server from a random coffee shop, that data is traveling across public, untrusted lines. Literally any intercepted packet could spell absolute disaster for a company. So how on earth do we safely transport corporate secrets right through the middle of a digital battlefield? Okay, let's dive into this. To solve this massive problem, we rely on our secure bunker, IPsec. Taking a 30,000-foot view here, IPsec acts kind of like a virtual armored truck. It doesn't just hide your data, it gives us three massive security pillars. First, authentication, so verifying the endpoints are exactly who they claim to be. No imposters allowed. Second, data integrity, making absolutely sure no bad actor tampered with your data while it was in transit. And third, confidentiality, using heavy-duty encryption so only the actual intended recipient can read the message. So, by formal definition, IPsec is a vendor-neutral set of standard protocols used to connect physically distinct local area networks. And what's really beautiful about this is that it takes these physically scattered pieces of an organization, like an office in New York, a branch in London, maybe a remote worker in Tokyo, and it weaves them all together. It literally makes them appear and function as a single, unified logical network over the internet. It's seamless. Here's our quick roadmap for this explainer. We're going to start with a welcome to IPsec VPNs, then we'll compare Phase 1 versus Phase 2, look inside the Phase 1 negotiation, navigate some network topologies, and finally wrap up with the IPsec configuration wizard.
All right, Section 1, welcome to IPsec VPNs and their operating modes.
Before two endpoints can even start their high-stakes secret handshake, they have to agree on how the data packets are going to be packaged. IPsec basically operates in two distinct modes. On one hand, we have transport mode. This mode encapsulates and protects the transport layer at above, but, and this is key, it does not protect the original IP header, and it adds no new header. So it's essentially unroutable once the VPN headers are stripped off. That makes it strictly for end-to-end, client-to-client VPNs. Now, on the other hand, we have tunnel mode. This is the real heavy lifter for routing traffic to a remote LAN. Tunnel mode takes the entire original IP packet, wraps the whole thing up, and slaps on a brand new IP header so it can safely route across the public internet. Moving right along to Section 2, Phase 1 versus Phase 2, the core of our secret handshake. And this brilliantly illustrates how the process works. Before a single drop of confidential data can flow, the endpoints have to engage in this complex secret handshake. The Internet Key Exchange, or IKey, systematically handles this. It doesn't just try to do everything at once. That'd be a mess. Instead, it systematically splits the heavy lifting of security into two very specific stages to negotiate what we call security associations, or SAs. Think of an SA as a really strict bundle of algorithms and parameters that both sides have to absolutely agree on.
To really grasp this, I absolutely love using a spy analogy. Phase 1 is all about building a soundproof meeting room. The outcome here is the IKSA. It's an encrypted channel created purely so the two parties can talk without anyone eavesdropping on the setup. Then comes Phase 2. Now that the spies are safely inside the soundproof room, they actually negotiate the rules of engagement for sharing their agency's top secret data moving forward. The outcome here is the IPsec SA, which dictates the encryption for the actual payload data flowing through the tunnel.
Okay, Section 3, inside Phase 1 negotiation. Let's see how that room is built.
We know we need this secure, soundproof room, right? But how is it actually constructed over an untrusted internet? Well, here is the terrifying reality. The initial connection between the initiator and the responder starts completely exposed, right in the clear. If they just started tossing sensitive keys back and forth right away, an attacker sitting in the middle could intercept them instantly. Game over. So establishing that initial secure IKS tunnel first is absolutely vital before exchanging any real keys. So here is the literal three-step magic trick of Phase 1. First, they authenticate each other, usually via a pre-shared key or a digital signature. Second, they negotiate a single bidirectional IKSA tunnel. And third, this is where it gets super fascinating. They conduct a Diffie-Hellman exchange. Diffie-Hellman is this crazy mathematical operation that allows the two endpoints to independently generate the exact same shared private key, without ever actually sending that key across the wire. It's like magic.
Even if someone intercepts all the public data, the math itself protects the final secret key.
So the crucial point is that you have to choose how you want to conduct this phase 1 handshake. If you're using the widely adopted IPsec version 1, you're choosing between main mode and aggressive mode. Main mode offers much higher security by encrypting the identity payload, but it takes 6 back-and-forth packets and requires a known IP address. Aggressive mode, on the other hand, is way faster. It only needs 3 packets, but it exchanges the pre-shared key hash in clear text. You absolutely need aggressive mode, though, if you're setting up dial-up users whose IP addresses change dynamically.
Before we wrap up phase 1, we really have to talk about NAT traversal. Think of this as disguised routing to get to our safe house. See, the protocol that carries our encrypted data, called ESP, actually lacks standard port numbers. Normal internet routers get incredibly confused by this and will just drop the traffic. The solution is NAT traversal. First, it detects sequentially if a NAT device is in the path. If it is, it cleverly encapsulates both our IK control traffic and our portless ESP data inside standard UDP port 4500 packets. This completely masks it, letting our secure tunnel survive the journey across normal routers undetected.
All right, Section 4, Navigating Network Topologies. Let's zoom out a bit.
Zooming back out from the packet level, how do these secure tunnels actually shape the architecture of entire organizations? First up, we have the hub and spoke topology. In this setup, all remote branch devices act as spokes, connecting back to a single central headquarters hub. So if branch A wants to talk to branch B, it has to bounce all its traffic through HQ first. This is brilliantly simple to configure, since branch devices only maintain one tunnel. But it does create a massive single point of failure. If that HQ router goes down, the entire company loses VPN connectivity.
Let's move to the next logical step and see how this builds into mesh setups. In a full mesh or partial mesh topology, branch devices are directly connected to one another. By bypassing HQ, you drastically reduce latency and take a huge strain off your central bandwidth. But there is a catch. The number of tunnels each device has to manage grows exponentially, which means you're going to need much more powerful and expensive hardware at every single branch.
The architecture trade-offs here are pretty clear, cleanly summarized right in front of us. You are essentially paying for the speed and immense fault tolerance of a full mesh network with massive configuration complexity and steep hardware costs. For a lot of organizations, sticking to hub and spoke provides the right balance, but it all comes down to what you actually need.
Finally, Section 5, the IPsec configuration wizard. Let's look at the practical side.
Understanding the theory of Phase 1 and Phase 2 is totally essential, but how do network engineers actually implement these brutal complexities on a daily basis? Well, modern systems like FortiGate use an IPsec wizard to basically abstract away the pain. Now, what's really interesting about this visual map is that as you choose your deployment type, the diagram visually updates to reflect your specific architecture. It completely masks the incredibly complex algorithm negotiations happening underneath.
The wizard effortlessly builds both the Phase 1 and Phase 2 configurations we just analyzed, and it does it in a smooth 4-step flow. First, you select your deployment template. Second, you input the remote gateway and authentication method, like your pre-shared key. Third, you define the local interfaces and subnets. And fourth, you review the automated address and policy summary. The system just automatically creates the underlying address objects, routing, and firewall policies for you. It's a real game changer. So we've built the soundproof room in Phase 1, we've set our data rules in Phase 2, and our packets are successfully navigating the hostile internet. But I want to leave you with a provocative thought. With your secure Phase 1 and Phase 2 tunnels established, who is actually trying to intercept your data today? The internet is constantly evolving, and so are the active threats on your own network. Stay curious, stay secure, and keep learning. Thanks so much for joining me on this explainer, and I will catch you in the next one.